Okay, can everybody see my PowerPoint?
Yes, I can see it. And let me go ahead and mute myself.
Well, thank you guys for having me. Thanks to students who showed up for the extra credit and the information. So I'm going to kind of switch gears here. I know everybody is keen on COVID right now, or COVID-2, as Jeff has informed us. But I'm going to shift gears a little bit, and we're going to talk about UFOs. Now, so to answer Trunk's question, this is the UFO room, but not UFOs like these. I always love showing this to my astronomy class and seeing how many people can get the movie or TV show that all of these aliens came from. Never had a single student pull that off. I've never even had a class together collectively pull that off because there's a couple of really obscure ones here. I am a product of the 80s. So I do want to see the chat window. Is there any way for me to do that?
Yeah, they should be on the right side.
Yeah, I see the video, but I don't see the chats.
Well, under the participant list.
It's okay. It's not a big deal. If you could just give me some feedback from what you're seeing, that would work.
Okay. Although, if you move the cursor to the bottom there are these bubbles that are showing up, the different colored bubbles.
Yep.
And one of them should be a chat window.
No, that's not wrong.
It looks, it's at the bottom and it looks like a balloon. And it should be, mine has
no big deal. On it. It's no big deal. It's okay. So let's do some brainstorming. I always love letting my students kind of dictate my presentations in a little bit of a way. What are the hot topics in astronomy? How many of you guys have ever taken an astronomy class for that matter? Feel free to chime into the chat. I'd like to know what, I see it up on the upper right. That's cool. All right, so feel free to chime in. What is interesting in astronomy? New life, I like that one. Life is always on there. That's why I had the slide just before. Anybody else? Wandering planets? Again, planets, trying to find planets, intelligent life, that's all going to be tied to life in the universe outside of our world. Anything else in astronomy that we're only interested in life? It's because there's a bio talk, isn't it? Right before me, living on Mars. I have a bunch of bio people here. I can see this already. Nobody else wants to throw one out there? Yes, future collision of us and Andromeda, which will be spectacular to view, but no humans will be harmed in the process of this collision. So I have a little list of things that I typically get from talks like this. Cosmology, that's one of my interests, the correlation between many planets and how it affects us. Exactly, extrasolar planets in the search for life. That is number one, usually with a bullet. There are typically two areas of astronomy that you have to tie your research to if you want to get funding. You've got to answer, are we alone? And where did we come from? Those are the first two bullets there. There's some other really cool stuff in astronomy that is a little lower on the list. Gamma ray bursts, they were a big mystery, the most energetic things in the universe. Black holes, everybody loves black holes. Dark matter and dark energy, what the heck are they? Which really ties into cosmology. Supernovae, anytime a star explodes, that's epic. And whatever, and Space Jam, thank you, Patrick. And as anybody who likes astronomy, it's typically for the pretty pictures, or as we refer to it in the business as astro porn. By the way, do not Google astro porn. I will not be held responsible for what you find. But it is the pretty pictures that sell astronomy. So I asked how many people have had an astronomy class, and I'm guessing, given the feedback I got, not terribly many. So let's start with the basics. On your upper left, that is a planet. That is Saturn. It is a fairly large planet, many times larger than that of the Earth. In the middle, not showing the corona here, but showing the chromosphere and a little bit of the lower corona, is the sun. Is taken through an H-alpha filter, basically a red filter. It only lets red light through. And by the way, when I said superheated, I meant it. That corona is 1 to 2 million Kelvin, and we do not understand how it gets so hot. Very interesting topic. But that's the sun. That thing is many, many, many times bigger than even Saturn. Size scale in astronomy is, I don't know what the conversion is, but it's millions of Fahrenheit too. So size scale is very tough to kind of convey in astronomy. I always love going, if you Google H-twins, scale of the universe, there's a really cool app where you can kind of scale from down, you can see the size of a virus. You can scale it all the way up to a galaxy. And you can see how small things are next to each other, because as humans, that's how we tend to perceive size scale, how big something is. We compare it to something else. The upper right, that is a star, and these all pale in comparison to this. This is the Milky Way. The Milky Way is a region of about 200 billion stars. It has what's in the center there, that bright portion is called the bulge. You have spiral arms going around the bulge. We are situated about halfway out. So the sun in this picture is smaller than a pixel. 200 billion stars in this artist conception, but the idea is our solar system is smaller than a pixel in this. Really, and if you think about that, just how big the solar system is, how far we are from the center of the Milky Way, 8,000 parsecs or 24,000 light years. It is an incredibly mind-numbing distance that even I really can't wrap my head around. I just know the number. I know it's big. And I'm going to be talking about stuff that is truly, quote-unquote, far out. Extragalactic objects. These are galaxies that are millions of parsecs, millions of light years away, billions. Dark matter, I'll have to save that for another talk, Mona. That's not my particular expertise. But these all tie into the whole picture of how we make the universe. I'll come back to that in a second. Okay, so that's a galaxy. Now, what's cool is at the center of every galaxy, this animation won't work very well. I tried it earlier, and it doesn't work. So what I'm going to try and explain here is this is a picture of the center of the Milky Way looks like in radio, actually. So these are a bunch of stars that are kind of milling about. And if you watch this one right here, what it'll do is it'll make this nice loop around that crosshair there. That crosshair is known as Sagittarius A star, and it is an active source of radio emission. And that star will pan around there and make a complete loop, or more specifically, an ellipse. Take an astronomy or physics, you know an ellipse is Kepler's laws, and we can figure out, based on how big the orbit is and how long it takes to go around, how big the thing is in the middle, how massive it is, how much stuff it's got. And if you do the math, and you watch that star go around, you get 4 million times the mass of the sun. 4 million times more massive than the sun. And it puts out no light, and the dot in the middle is about the size of our solar system. There's no other way to explain it. It's a supermassive black hole. And every galaxy has one. In fact, we finally have a picture of one, or of its shadow. This was taken last year. This was epic. I walked into my astronomy class after seeing this. I might have dropped an F-bomb. Don't tell the deans. Oh, wait, this is being recorded, isn't it? So this is a picture of the shadow created of light around the supermassive black hole of M87. It is an active galaxy. There are plans to get an image of the black hole in the Milky Way. It's just this one was much bigger, and because it has light around it, it's easier to get the picture of the shadow. So we now actually have a real image of a black hole. We know what they look like. We know they're there. And every galaxy has one. This is Able 22 something. This is a picture that Hubble took, the Hubble Ultra Deep Field. And every dot you see is a galaxy. I don't immediately see any. I see one star over here. This is a star. I don't see any others in this image. I might be missing one. But you know it's a star because it has that crosshairs. Every other dot is a fuzzy image. Those are galaxies. 200 billion stars per fuzzy blob here. Yeah, and all of them have a supermassive black hole. Okay, now galaxies we often take spectra of things in space because astronomers really have one option. We don't get to take a virus like COVID-2 and put it in a petri dish, change something, see what it does. We don't have that option because we just kind of have to wait for them to do their thing. And the only way we can interact with them is through their light. So what we do is we take their light and we spread it out using a prism. And we map that out two-dimensionally. How bright is it for every wavelength? And this is a collection of stellar spectra because, as I've said, galaxies are made out of 200 billion of these guys. So it would make sense that their spectrum is an amalgam of all of those spectra, basically weighted on how many of each type of star you've got. Well, eventually we started taking spectra of galaxies, and we got some that look like this, which looks nothing like what you just saw. These have emission peaks, and their emission peaks don't line up with or didn't line up with our picture of atomic spectroscopy was back in the day in the 50s and 40s. It was a real problem. But after 50 so years, we finally figured out exactly how this works. This is nicknamed the Exploding Bagel by Todd Henry of Georgia State University. And what we eventually realized is the emission peaks were out of place because of Doppler shift, and that you're actually looking at hydrogen lines. I've overlaid the hydrogen emission spectrum. We have labs where you literally look through a spectroscope at heated tubes of hydrogen, and you'll see those lines, or at least the first three. The purple ones are awful tough to see. And we saw different types of galaxies with different types of emission spectra. So on the left, you'll see the two different types of emission spectra that were famously categorized by Carl Seifert. Carl Seifert gave type 1s and type 2s, and the canonical example of a type 1 is NGC 4151, of a type 2 is 1068. I don't want to spend a whole lot of time breaking down the exploding bagel and all the pieces, but suffice it to say that the exploding bagel, it's a mess. There's a lot of stuff going on there. There's an accretion disk of material feeding the black hole that can outshine 200 billion stars in a galaxy. There's stuff spinning around very, very rapidly down close to the black hole because it's deep in the gravitational well of the black hole. You have to move fast or else you fall in. Stuff that doesn't move fast falls in. There's stuff out further that doesn't move as fast because it's not as close to the black hole. It doesn't require that kind of speed. So it kind of sits and mills its way around. There is a giant, what we call donut or torus, that's centered around the accretion disk of the black hole. That's basically a brick wall of dust. So if you're looking from one way, you wouldn't actually see the black hole. If you're looking from kind of down into the left, you wouldn't see the black hole, the accretion disk, or these high spinning clouds. You would only see the slow spinning clouds up here. If you were looking from kind of top down at the whole of the donut, then you get to see everything. NGC 4151 is the everything. NGC 1068 is the side view. And this applies to many, many different types of AGN. Okay, now that I've explained planets, sun, stars, galaxies, supermassive black holes, and AGN, I don't specifically study any of those. I know that's kind of funny to hear. What I do study, though, are the absorption lines in AGN. So on the right is a pixelated mess called NGC 3516. It is an AGN, active galactic nuclei. So basically it's a galaxy, and down in the middle of it, its supermassive black hole is eating things. It's eating gas and dust. So it looks like a type 1 style Seifert galaxy, or AGN. So it's like the NGC 4151 there. However, it has absorption lines on top of the emission lines. Now, these absorption lines are because black holes are messy eaters. I showed you the exploding bagel. It's a mess of gas and dust all over the place being slung around. And some of that stuff can get slung out and ejected from the vicinity of the black hole, not from inside the black hole, but from stuff nearby it before it ever gets in there. It can actually get close and get pushed back out because light can push on things, and you've got a really, really bright light bulb down there. And as that stuff is moving away, you get light moving through it, and you absorb some of that light. And in most of the things that we see, so on the left, the letters there, that's Lyman alpha, that represents hydrogen. Nitrogen 5, that is nitrogen 4 times ionized. That means you've stripped off 4 electrons. This is high temperature stuff to the tune of 10,000 Kelvin. Carbon 4, this is carbon 3 times ionized. So for the chemists in the room, that would be C+++. It's really, really high energy plasma. And we see the absorption lines, and they're always blue shifted. So Doppler shift, you guys all familiar with the Doppler shift, the vroom, as something passes you, right? So this is the blue shift. It's approaching us, so its wavelength gets shorter and looks bluer than it would. We always see that because it has to be between us and the source, and it is always moving away. What do we know, or why do we care about these? Well, this picture is a model of our universe. This was known as the Millennium Simulation, Frank et al. 2000, coincidentally, millennial. So they basically put physics and gas in a box and hit go from the point zero after the Big Bang and watched how it evolved. And we got something that looks a lot like our universe. This actually doesn't look too far off if you look at a kind of cosmological scale where all the galaxies are, they're clustered. But the problem was the galaxies were too big. The black holes in the galaxies were too big because there is a direct relationship. The bigger the black hole, the bigger the galaxy, or more specifically, with spiral galaxies, that bulge I mentioned, the bigger the black hole, the bigger the bulge. It is a 1-to-1 relationship. They are tied intrinsically, and their simulation couldn't model that. So what they figured out is that there had to be something stopping the black hole from growing and taking that material and putting it back into the bulge. Well, our outflows are really good at doing that. This is a picture, it's a composite picture of Circinus, which is a galaxy fairly close to us. Now, you see the red stuff kind of moving away polarly, because you've got kind of a flat plane and a piece going up into the left and a piece going down into the right. That was actually triggered by star formation. Lots and lots of stars can have the same effect. But it's basically what we imagine these outflows that we see to look like. What do we know about these outflows? Well, I've been working on them for about 15 years, and we got some pictures, not physical pictures, but some idea, because all we know is we see the absorption lines. We don't have actual pictures of this plasma. We don't have pictures of what this gas looks like or how big it is. We have to infer everything from those absorption lines. It's not easy to do. We know about how big they are based on how frequently we see them. We know about how far away they can be based on some of the physics of those lines. The velocity is pretty easy to get because the blue shift, the Doppler shift, tells us exactly how fast they're moving. Structure, density, how fast they're moving left to right across our line of sight. We've got pieces of evidence to kind of support all of them. And ultimately, we're looking for the amount of energy ejected or the amount of mass ejected from the vicinity of the black hole. And we've got a lot of that mapped out. In fact, some of them were kind of surprising. This is a picture of what we think an outflow might look like if you went there. So this is a real image. You've got all the galaxies in the background. The big purple blob is another elliptical galaxy. And then we've had an artist draw in kind of those big bubbles being ejected from the AGN. Those are the winds. And we made them so big because it turned out that a lot of these outflows we were seeing in some of the bigger AGN were at kiloparsec distances. That means that I've kind of mapped it out. We saw lots of outflows down where the first green one is, where it's a Seifert outflow. It's in the vicinity of the black hole. It makes sense. It could be ejected a few parsecs, hundreds of parsecs. But we were seeing them ejected thousands of parsecs. Imagine plasma ejected from the nucleus of the galaxy sweeping by the sun. That's how far these things are going. So some of these things were quite startling. But it required an immense amount of effort to try and understand simply from absorption lines. I keep driving that point home because it's going to be pertinent to UFOs or ultra-fast outflows. Hammond et al. Came up with a laundry list of kind of requisites to say that this is a bona fide outflow, something that is in the vicinity of the black hole that has been ejected. It's not easy to do. It's the bottom line here. We need to know that it's something close to the quasar and not something kind of between the Milky Way and the AGN. There's a lot of space between the Milky Way and the AGN. We're talking millions of parsecs, millions of light years. There can be clouds between us and that object that could mimic these lines. And so Hammond et al. Came up with this idea, okay, well, if it was an intervening thing, if it was something between the Milky Way and that AGN, then it would have this property. If it's intrinsic to the AGN, it would have this property and this property and this property. And we didn't count them to be true intrinsic outflows until it met multiple of these criteria. And here's an example of one of them that I've worked on. This is NGC, I take that back. This is NGC 3516. This is carbon-4, and you can see it's got multiple troughs, and they're very, very deep, where I've marked C4 1548. That's 1548.202 angstroms, and it has its twin at 1550.770 at angstroms. And you can look at these lines and go back to Hammond's arguments and see these are clearly tied to it. But not only that, if you see carbon-4 there, you can go over to other parts of the spectrum and look for silicon-4. You can look for hydrogen. You can look for nitrogen, and you'll see signatures at the same speeds in all of these, which helps verify that this is a bona fide intrinsic outflow to your object. So same example, this is silicon-2 from NGC 3516, situated about 1270 angstroms in the observed frame. So that is a signature that matches carbon. And we've got one for alignment, and we've got one for nitrogen, and we've got one for oxygen-6, that's oxygen 5 times ionized. And we've got all of this corroborating evidence to say this is not something intervening, this is something intrinsic. Now, enter 2018 and Clyde Tombazy. He is kind of a revolutionary in X-ray AGN right now. He's came up with an object where he saw an outflow, and now most of the outflows that I've studied, the fastest I have personally worked on is about 10,000 kilometers per second. That's pretty fast. Tombazy was seeing outflows in the X-ray data that got up to, half of the speed of light. And a lot of AGN experts were like, that we've never seen that. Why are you just now seeing this? Oh, because we now have X-ray data. Well, X-ray data is not exactly the best. It is highly, how do I put this nicely, very low signal to noise. They don't have a lot of light that's emitted in the X-rays to pick up. So we're not sure we trust their signals. And he was saying that it was iron 24 times ionized that he was detecting. But that makes sense because these can get really, really hot, millions upon millions of Kelvin near the vicinity of the black hole. So if this gas is really, really close, it'd be really, really hot, and it'd be pushed on a lot, so maybe it's moving at half the speed of light. But a lot of astronomers, like one of my bosses at Virginia Tech, he was my postdoc advisor, he vehemently was, this can't be real. These UFOs just aren't happening. You're seeing stuff in the data that's not real, especially since the line would be there in one spectrum, not in the next, or it'd be in a different place, and the velocity is changing all over the place. That's not what we see in any other type of outflow line. Now, he would only see it in iron, what we call iron Lyman alpha, or iron 24 times ionized. Now, we've started getting better X-ray data where they'll see a line from iron and then they'll start to see lines from other things like sulfur and magnesium. So it's starting to become more corroborated. But the catch here is I got a call from one of my friends, Steve Kramer. He's an AGN expert. He's like, so Dunn, Tom Basie was claiming that PG1411 has a corroborating UV line. So not only are they seeing it in the X-ray, but they're now saying they see it in the UV. You're an expert when it comes to FUSE. FUSE was the Far Ultraviolet Spectroscopic Explorer. It was a satellite we put up. It was the little satellite that could. I can tell you that story sometime. But he's like, have you gone through the data? Have you looked through FUSE to see if you see any UFOs in that data? No. So I put a couple students to the task, sent them out looking. And when we looked at PG1411, what we found is that they don't know UV data well enough yet. They're good at X-rays, not at UV, because what they claimed was a UFO in PG1411, the signature matches perfectly with a very low velocity outflow that we knew about in PG1411. So I've got a map here. Again, the LY is for hydrogen. So it's about a 400 kilometer per second outflow that agrees with an oxygen doublet. It's visible in all three of the lines of hydrogen that are detectable by FUSE. It's visible in carbon twice ionized. So they got their signals mixed. And here's the other thing. We've been going through FUSE data for about a year through all of the objects we have access to, and none of them have shown a UFO. So does that mean UFOs aren't real in the X-ray data? No, they could very well be real. Does that mean we're seeing them in the UV? Not yet. I'd be very hesitant to say we've got an agreement between a UFO detected in the ultraviolet with a UFO detected in the X-ray. So right now I'm kind of on the fence as to whether I'm confident X-rays or the X-ray UFOs are real. And to get to your point, Jeff, I saw that question pop up. How did they take the findings? Tom Basie's a pretty easygoing dude. I'm pretty sure Steve has kind of shared that with him, but we've not published this yet. Being in academia at a institution where teaching is primary focus, I've not had a chance to publish it. I did get a paper out last year. I hope to publish this in the next year or so. We'll see what happens, but they've shared it at conferences from what I've heard. But that's kind of my story on UFOs. Thank you so much for everybody, and if you got any questions, I'll be happy to take them.
Well, thanks so much, Jay. It was a great talk, and I'm really happy to see that there's actually active research at our institution.
And if I can throw out a kind of an invitation, I've had about 35 students come through my research team, and I'm gonna need some more because a couple of them have moved on. One graduated, is going to grad school now. One is a senior and she's getting ready to go to grad school. I'm always happy to entertain it. If you're just interested in how research is done, I've worked with people who are not even astronomy majors. So
go sign up with Jay.
Now, I did see some questions that I didn't get a chance to answer. I wanted to make sure I didn't go super long. Faculty could participate, absolutely. David Yenneral has worked with me a couple of times on projects. We've gone to AAS meetings and stuff. Where do you get the spectra? All of the spectra that I showed there were FUSE. Most of my spectra these days come from either the Hubble Space Telescope or Sloan Digital Sky Survey. Those are two archives that are online that are completely free. Anybody can download their data and go through looking for stuff. Let's see. Dark matter's composed of particles that do not reflect. That is true, Daisha. There's not a question there. But we don't know what actually particles are doing that. Okay, that's all the questions I see immediately in the chat. If there's no other questions, anybody?
Well,
Unmute.
all right. Well, thanks again, Jay. Maybe you can put your email address into the chat box in case people have questions later.
Jay, can the students do their research with you online? How are you doing that with this whole issue?
So my current student, she's actually taking Phys 4900, which is a research credit with me. She was my physics student from 2 years ago. She's still doing work with me. We've been meeting by WebEx kind of once or twice a week where I'll give her a task. She'll come and bring it to me. More than likely, it's show me the problems with the programming and I have to explain why. But yeah, we've been doing WebEx for right now. And yes, you can do it online primarily. And even during the semester, most of the time we would meet on Friday for about an hour and get updates and new tasks, and then they'd have a week to go do their business and bring it back to me the following Friday. So good question.